So let's talk about the powder-based metal additive manufacturing processes. So there are a few steps for the powder bed fusion process. The first one is you need to spread a thin layer of metal powders, and then scan an energy beam over the regions of powder you wish to melt, either laser or electron beams. And that's a generation of one layer. And then you spread this process to create the following layers. So that's the major steps for a powder bed fusion process. As you can see here, the metal powder additive manufacturing has been uh, advanced a lot, especially in the marketing point of view, because in many industries like aerospace, airplane, or biomedical, people are looking for a process which can produce lightweight and complex geometry part, and which metal additive will do the work. So there are a few key components for the for the powder bed systems. First of all, the powders, right? Powder source, how you handle the powders, and you have a build tank, a waste bin to contain the excess powders. Also, energy sources. That could be laser or electron beams and so on and so forth. There are also motion systems, subsystems like energy beam steering, build platforms, powder spreading, and so on and so forth. Also, there are some acronyms: the direct metal laser sintering, direct metal laser melting, selective laser melting, and electron beam meltings. Um, so for a selective laser melting, basically, the first step is prepare the slice, load the powder, and then there will be the spread, powder, melt, and repeat these two processes for each of the layers. Of course, you need to depowder the part after the part is built. Remove the part from the platform and do the inspection. Also, there could be some fine-tuning, surface finishing using the machining process. Let's look at this video. Actually shows the whole process of the SLM process. Okay, let's continue. So this the direct metal laser sintering process is launched by the EOS, which is a European company, in 1995. So the uh, the uh, the advantage for this process is the accuracy is really good. Also the density. You can see here it gives you a 20 micron resolution for the part. But there are many weaknesses as well for this process. First of all, it's a cold process, meaning during the process the powder bed is not heated up. So that introduces a high thermal stress. Also, the building speed is relatively slow. Um, Another thing is the uh, atmosphere need to be controlled. Usually, uh, we need to have a argon or helium gases filled in the building chamber. So there are a few challenges during the powder spreading. So first of all, let me maybe I just draw some illustration figure. Let's see, this is the powder bed, and you have the roller, and here is the powder, right? So let's see you let the roller rotate in this way and move in this direction. So what happen is actually you will maybe let me draw another line. So maybe you will smooth out uh, some of the surface, but after the roller roll uh, from here to here, there will be some small uh, bumps generated. So instead of rotate in a clockwise direction, actually this roller tends to rotate in the counterclockwise direction, such that if there's some bump, so that will make the surface smoother. So that's why we need a counter-rotating roller. Another thing is because there's a thermal stresses, the part could be deformed. Let's say it's not a after one layer is built, it become a little tilted. It's not a flat surface anymore. So if the roller moves from this direction to this, I mean this way to this, that could be some collision happens, right? So that's why sometimes some design use the blade, a flexible blade for the collision. So for the blade, let's say you have a, let me draw another illustration. Okay, let's see, this is the deformed part, right? And there's a blade. So because the blade is flexible means when it contact with this part, it could be deflected like this. Then uh, you can still move the blade without a start over here. So that's why um, a flexible blade will be adopted to avoid the collision. Another thing is the recycles of the powder. Because the powder is so expensive, so you cannot just use every time just use the new powder instead of recycling them. That will bring the problems for many applications in the aerospace or biomedical because they require the tracing of the material. Because you are mixing different material, different powder together, that makes the tracing uh, very difficult, right? So some trends for the equipment. First thing is the size of the machine becomes larger and larger. As you can see, those ones are really big, right? So it could produce the big part. Um, Also, because the building space is so big, one laser beam is not good enough, so they tend to use multiple laser. Um, Also, the powder handling is integrated and automated, so it requires very little human involvement to handle the powder, because the environmental issues, many safety department just do not allow human to be highly involved in the powder handling because it's an environmental hazard process. Also, the speed is increased. Also, the power used in the process is pretty high to make sure the metal could be melt and fused. Um, but for the building area, something like, I mean, building volume, something like this, if we use the titanium material like this, Ti 64 alloys, so if we want to fill the whole tank of this machine, it turns out it requires 1.3 million for just the powder. So it's a very expensive process for building part using such a large machine. Another thing is the temperature, because the temperature will be essential to control the quality of the part. So this new equipment tends to monitor the temperature in real time. Here shows some parts built by the machine, the SLM machines. So as I mentioned, there will be the thermal stress introduced to the part. If you look at this, see, basically that's the building plate for the part. So this one is the part, and this is the plate. So you can see this plate is bended because the thermal stress introduced on the part, and it drive the plate to be deformed. So that's a really serious problems for the direct metal laser sintering process. So if definitely you do not want to spend 22 days and around $75,000 and turns out have some result like this, right? You definitely don't want to have it. So that's the essential problems need to be solved for the process. So here gives you some ideas how you remove the part from the build platform. So basically, there's a process called the EDM, or the sparkle machining process. So basically, the a very thin line would be used to remove the part from the building platform. There will be a small sparkle generated as a blade to cut the part from the build platform. If you look at this zoomed view, so this is a wire, and there will be spark generated to cut the material, and such that you could cut the part off from the plate. So another process is this electron beam melting process, and here shows a machine from the Arcam. So this company is originally established in Switzerland, and now is acquired by the GE Additive. So basically, it utilized the electron beams instead of laser to melt the material. So the strength for this process is, again, it could produce those full dense metal part, and it has a hot process, means the build platform will be heated up such that the little thermal stress will be introduced. And also it's relatively faster compared to the selective laser sintering. Also, it has some weakness. First of all, the chamber need to be vacuumed. Means you need to pump the air out from the chamber, which requires a time. The material is also restricted. For this EBM, basically you can only use a few material which could conduct electricities. For the nylon, I mean plastic or ceramic material, you cannot utilize. But in the selective laser sintering, you could use plastic, um, ceramic, and metal materials. So that's the big difference between the EBM and SLS. So basically, for the process similar to the previous one, a thin layer of metal powder is spread over the platform, and then the electron beam is selectively scanned over the powder bed such that the powder will be melted. And then next layer of powder is spread, and this process will be continued, will be repeated. Let's look at a video. Okay. Also, let's look at the melting uh, of the, I mean the electron beam melting, and see how it looks like. So basically, it shows a biomedical applications for the implant. As you can see, the electron beam is like you have multiple energy sources, multiple electron beam scanning, but actually there's only one. I will talk about why it looks like this. And here shows some very nice part made by the electron beam melting. So as you can see here, we have the a spread, I mean a actually it's like a blade-like mechanism to spread the metal powder. Again, as I mentioned previously, this kind of design will prevent the collision. And another good point for this is it could spread the powder two ways from both the two directions, right? And here shows the electron beam guns. So basically, the current is passing through a tungsten electrodes. Basically, it talks about this part, and high voltage is driving those um, uh, electrons and make it pass through this part. So for here, there are magnetic coils, electromagnetic coils, and these coils could change the direction of the electron streams to up and right, up and down, left and right, such that you could uh, steer the electron beams into different location on these surfaces. So there's no actual mechanical motion during this process. It's all the change of the electron beam controlled by those coils. So the benefit is it moves very fast, um, and the high-speed steering could be achieved. Usually, it could reach the 100,000 meters per second. So that's why you are looking at when you're looking at the video, yeah, it just like several electron beams is scanning. Actually, it's just one. That's the illusion because it the visual illusion we have because the um, uh, speed of the electron beam is so high. So also there are some uh, parameters for the EBM process. The V represents the spot velocity, and D is the spot size. Also, P is the beam power. And there will be a melting zone generated, melted by the electron beam. Here shows the traces to generate the contour. Of course, the different tool paths, different such kind of a trace would affect the mechanical properties of the part, and that's also a very important point for the manufacturer of the EBM machines to look at. For the building material, the EBM process also use a very expensive material for the near net shape part. Um, but it could, I mean, both the machine and the material are very expensive, and they could produce the near net shape parts with complex geometry. And that's a need in many applications like the airplane or airspace area because they need to produce the part with a highly complex geometry there for the weight reduction, and that is very important for those applications. So the cost will be justified in those applications. Another thing is um, for the EBM process. So the ceramic or polymer powders cannot be used because when the electron beam hit on the um, powder bed, it will be conducted to by the metal powder, and the elect and will be led to the ground. But for the polymer or ceramic, they are not good conductors. They do not have good electricity conductivities, such that the electron beam will go nowhere, such that will charge the particles of the material, and because they all have the positive charges, I mean negative charges, then they will repel each other and make a dust filling the whole chamber, which is undesired. So that's why only those material with good electricity conductivity will be used in this process. Also some um, parameters, I mean some dimensionalities for the beam and melting pool diameters. So approximately the electron beam has a spot diameter 0.1 millimeter, and the melting pool will be roughly 1.2 millimeter. So what's the advantage to having such a powder spreading mechanism? Because it would allow the spreading of the powder from both sides for saving the time. Another thing is why there's a necessity to pull a vacuum with electron beam system and not laser system. That is because for the electron beam system, if there's air, gases there, the electrons will hit the gas molecules and lose focus on the surface of the powder bed. And another question is about why the powder bed is preheated. That is for reducing the thermal distortion or thermal stress in the material by heating up the powder bed. Another very interesting point, question is why the powder around the part are partially sintered. Because the centered part, the powder will conduct the electricity better compared to the loose powder. So that's why those powder around the part will be centered. Also, if the powder is still very hot and the door of the chamber is opened, then the powder will be oxidized, which are undesired. And for the machine, from the machine design point of view, if there are see-through viewpoint over there, you need to make the window to be a leaded glass part, such that that will protect the user's eyes from the X-rays, because when the electron beam hit on the metal, there will be the X-ray generated. Also, again, the spreading powder using the blade, that is for allowing the slight distortion without the collision, because this blade is flexible and could be deflected. So when you need to blast off the excess powder, what's the material you want to use? So definitely you want to use the same kind of metal powder as one to build the part, to avoid the cross contaminations. Because if you use different material, definitely that will make the powder mixed with other material, that makes the quality of the part even unreliable. And also, there will be a small amount of helium gas fed into the chamber over the powder bed. Of course, if you have some helium gas there, that could make the electron beam hit onto the molecule of the helium. But that's the minor effect, because the amount of helium is really small. But the more important thing is because the electron beam is hitting to the molecule of the helium, and the electron of the helium will be knocked out, such that the helium gas will becomes a positively charged, and it turns out it will neutralize the negative charge of the powder bed after the electron beam hit onto the powder. And basically that's the charge neutralizer for this process. Some analysis of the melting, and the beam velocity varies from 10 to 1000 millimeters per second, and layers usually 1.1 millimeters thick. Um, and and also there are some other parameters like the powder beam, spot size, and scan speed that will determine the concentration of the energy delivered per unit area and per unit time. So here gives you a equation about the depths of the melting pool, melting depths, or we use Z to represent this melting depths. And what you need to know is this beam power, this temperature rise during the process, and also the thermal conductivity, beam diameter, beam velocity, density of the material, and also a specific heat. Basically, once you know all these values, you just substitute to this equation, and turns out you will have the melt depths. A very interesting, a very important thing is before you do the substitution of all these known parameters, be aware of the units, and that's the always case. You need to be careful when you do some calculations. So here give you an example to compute the depth of the melting pool. So there's only one thing I want to mention, that is for this density. Basically, it's the solid density, which is not the powder density. So we need to do a little computation here. Basically, we assume the loose powder will have not much more than 64% of the density of a solid. That means you can use 64% of density of this solid density as the powder density to be substituted to the equation. And again, you need to be aware those unit during the computation, and that's it. So here gives you, sorry, here gives you the result, which is 0.75 millimeter for the melting depth. So there are some problems for the melting, because we are, I mean, the process is in the vacuum environment. So there could be some evaporation happens for some of the elements of the metal powder, and also is the temperature at which an element vaporizes different under the vacuum than it is at the ultimate spheric pressure. And the answer is definitely will be affected. And let's look at specific cases. So we have the 7075 aluminum, which are the alloy with the aluminum, zinc, and magnesium, magnesium, yeah. And basically, these are the three elements in this alloy. And let's say this alloy is melted at 100 C and a vacuum of the 10 power by 3 torr. So what will be? Is there any concern about the vaporization of the three elements? So we need to look at this curves. So here gives you the vapor pressure in the unit torr, right? So we need to look at we need to look at this line, which is the given, right? Oh, sorry. And also the melting temperature is something like this, right? And then we need to look at the curve of zinc and this Mg, right? Then you will have the point, two intersection point of the curve with this temperature, and you can look up the temperature. I mean, look at the temperature that is 300 C, and this one's around 400 C. But but the melting temperature is 1000. So that's definitely a concern that these two um, elements could be vapored before it's even melted. So that's the way how you check is there any concern about the evaporation for the different elements in an alloy. Um, Also for the shrinkage, what happens to the part as it cool down? It will shrink. Also, to compensate shrink, you want to scale up the size of STL file when you build the part, sorry, using the EBM machine. And there are some reference numbers for the H13 tool steel. Probably you need a factor of 1.4 percentage of the scale up. And for this titanium alloy, probably you need to specify different scaling factors in uh, uh, different directions. Um, Also, another point is the cooling of the steel material, and the speed, how fast you cool the material will affect the mechanical property of the part a lot. And basically, you need to look at this time temperature transition curves. So here, this temperature is the function of time, and you could see different curves that shows you the different status of the same same material under the different conditions of the cooling. If you cool the parts rapidly, there will be a it follows a one curve, and if you cool it very slowly, there will be another curve, and you will have all different material property over there. For the cooling of titanium, it's very dangerous because it uh, easily oxidize, and that could be a explosion or a fire if you do not cool it uh, carefully. So first of all, you would like to either cool it in the vacuum or cool it in the heliums. If you cool the titanium in with the helium gas, it will speed up the cooling from 10 to 12 hours down to only 2 to 3 hours. Definitely you want to have a much faster cooling, right? Um, for the post-processing, the centered material need to be removed using the air chisels or wire brushes or some bead blasters. And also the loose powder will be vacuumed away. Uh, but for the vacuum machine, definitely you want to use this explosion proof motors because you are dealing with the powders and there's a risk to have explosion. Um, Another very interesting topic is the design for the EBM uh, part. So usually you need to do machining after the building. So that's why you want to add 1 millimeter additional material on the critical surfaces because you would like to machine it after the building process, right? For the facility of the EBM machine, because it utilizes the electrical magnetic field to control the electron beam, such that you do not want to have a magnetic field to affect uh, their part, the EBM process. So that's why you always want to control the magnetic field around this machine. Here shows some surface finish of the part. And basically there's some information about the minimal wall thickness, the machine size, and also some accuracy and so on and so forth. And here lists some of the raw material you could use in the uh, uh, building using the EBM process, and some of the size information over there. So another thing is you want to tweak those parameters such as the power and the velocity and figure out what are the best condition, optimal condition you use during the printing process. So for example, if we look at the velocity and the power, so if you tends to have a high velocity but a lower power, then you will have these beads, right? Patterns generated. And in contrast, if you want to have a high power but lower velocity, what you end up have is these dips. Of course, you do not want to have both of the cases, and something in between will be desirable, but that requires the experiment by manipulating the different, set up different velocity and power combination to have such kind of mapping or curves. Basically, this is just a macroscoped image of the building part. Another thing is the powder. Definitely, you want to have a nice powder. So uh, for the powders, uh, what is desired is more like the perfect sphere is better. For something like this blob shape, which is irregular blob shape, is undesired for the building. So definitely you want something like this, this, and this. Also, how to characterize the powders. Basically, you need to find out the ratio of the powder particles width and height, and such that it could be characteristic. Sorry, by looking at these parameters. Also, the porosities. During the printing process, definitely you do not want to have those void in your building part, because the pores and the voids will be the stress concentration sites or the crack initiation sites. Means when the load applied, the 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 crack will be highly possibly happened uh, well, with this, near these regions, which are not desired, especially in some of these um, aerospace or airplane applications, or even the biomedical applications, for example, the implants, right? So here summarize the different aspects of laser and also the electron beams printing process. So they are both expensive and high energy consumption. One is the for example, for the laser based, you do not need to worry about the electrical conductivities, but the electron beams ones only can use the material with the good electrical conductivity. But for the laser one, you need to think about the optical reflectivities, because it's an optical based process. Energy efficiency, the E-beam has much higher efficiency, um, but for the atmosphere, lasers usually need those argon or helium gases, but E-beam is pretty much the vacuum. And the safeties, there will be UV light produced in the laser process, and the X-ray produced with the electron beam process. So you need to protect the users from these two kind of hazards light. rays or lights. um, Also, some personal opinion, the e-beam system are very expensive to be used on those polymers. So the inject or extrusion-based ones are more safe and cost-effective. Um, I mean, I'm not talking about an e-beam. I'm sorry. It actually is the energy beams means either laser or electron beams are too expensive to use, right? Also, the high power laser best for the ceramic and very small metal parts. It's not good for the big ones, as mentioned previously. The electron beams are the best for the metal and metal matrix composite, and that's some of the opinions for you to think about in which scenario you should use what kind of process. Some of the research issues, for example, how you make sure the part quality produced using those powder bed fusion will be as same as the one produced using other process, and how to enlarge the building size of the part, how to avoid the voids and the inclusions during the printing process. Again, the qualification will be a very interesting, I mean, will be a very big problems for many of the applications, especially when you talk about the airspace, airplane, and bio ones. You have to make sure the build part will be as good as the one built using other manufacturing process. And how to recycle the powder, right? Because the powder is so expensive, definitely you want to find out a way to make the best of recycling for the powders. And yeah, that's pretty much the all for the metal additive manufacturing.